look at this. This is what is the example, and how the tail recursive function actually works. So there is something called as tail. So you know that every functions has some body to it. That means it comes with some set of statements. What is the job of a function? To perform this set of statements. If in those set of statements, if the last statement is your recursive call, the last statement of that function, okay, such function is called as tail recursive. That means when you reach the end of the function, you're going to make a recursive call. Such function is called as tail recursive function. So carefully observe here. A recursive function is said to be tail recursive if the recursive call is the last thing done by the function. Okay, so when you see this particular function, a main function is calling a function called as fun with a parameter as 3. Okay, and when you see, this is a function definition, and in this function definition it has got so many statements. It has got so many statements in it, and if you see the last statement, which is represented in black color, where we are calling the function within itself. So the same function fun is called within fun. When it has been called, it is called as a last statement. Such functions are called as tail recursive function. Okay, and there is one more statement written along through its definition. That is nothing but there is no need to keep track of previous state in tail recursion. That means, you know that when the problem which we have solved, for example, fib of 3, if you say Fibonacci of 3, let us go back to that problem and just see how the Fibonacci of 3 was approached. So look at this. If the Fibonacci of 3 was called as a parameter, the 3 as a parameter to Fibonacci function, it didn't give it directly the answer. The Fibonacci of 3 was saved until Fibonacci of 2 plus Fibonacci of 1 was solved. Because what is Fibonacci of 3? It is a sum of previous two numbers. So it should solve Fibonacci of 2 plus Fibonacci of 1. And what, see, directly Fibonacci of 2 plus Fibonacci of 1 cannot be computed because Fibonacci of 2 is not a direct answer. That means it has to go to the general case and again divide that problem into smaller instances. So Fibonacci of 2 was converted into Fibonacci of 1 plus Fibonacci of 0. That means you can see that in each phase, when the problem was subdivided into smaller instances, we used to maintain the state. Okay, so once you get the base case answer, each state was resolved. Okay, if you get return 1 and return 0, then only you can solve Fibonacci of 1 plus Fibonacci of 0. If you solve this, then only you will get the answer for Fibonacci of 2. That means in every recursive function, what you have seen till now is the state was maintained. But when it comes to tail recursive function, the definition says that it is a last statement which has been mentioned, but there is no need to keep track of previous state. There is no need to keep track of previous state. So whenever you call a function, you get the result directly. Okay, you need not get into the phase where you need to keep track of previous state. So when you see this diagram, what it actually means is this is called as stack activation record. So usually all the recursive functions go through a data structure called as stack. All right, or any functions, if you see, they just be pushed into a stack data structure. So that means, you know that when this program runs, the first function which gets into the role is main function. Okay, so what happens is this is a stack data structure, and you can see that the main has been pushed. Pushed means it has been inserted into the data structure, that is called a stack activation record. So main start executing, that means it has to be activated. So this is what is activation record. Act M means activate main. Okay, and once the main is activated, inside the main what you have called is fun of 3. So the next function which will be inserted to the stack will be fun of 3. So you can see that the next function which has been inserted is fun of 3. So activate fun of 3. So once it gets activated, you go into the instructions inside this particular function. So what is happening? So 3 is copied to n. So it checks if n is equal to 0. It's not equal to 0. Then it goes to else case. And in your else case, what you are doing is you are printing the value of n. Okay. So print the value of n. What is the value of n? N is 3. So the output currently is 3. Okay, and then again carefully see return. So after if and else, since it's else block, it prints this statement, but this does not end the function because we have the last line of the function. What is in the last line? We are calling the function. We are dividing the problem into smaller instance and we are calling the same function. It was 3, that is n was 3. Now we have become made it n minus 1. So it has been reduced. But look at that, the recursive function has been called at the last tail of the function. That is why it is called as tail recursion. Now, fun3 did not waited it to become fun2. Fun3 gave you the result directly as print3. That means there is no need of keeping track of previously. Fun3 need not wait till fun2 or fun1 or fun0 gets its answer. It can directly give you the answer. Now, since we have called return in the last line, what is the function we are calling? We are calling again fun, but the value is been changed. Next function which will be inserted to the stack will be fun of 3 minus 1, that is fun of 2. So you can see this diagram, the first diagram. So main is pushed, fun of 3 is pushed, now it is fun of 2. So when fun of 2 is pushed, the value of n is copied as 2. Okay, so again it checks, is n equal to 0? No, it's n is not equal to 0. So it will go to else and print the next value, that is 2. Okay, so it prints 3 and 2. Sorry, this should not be a new line, it should be a tab because we are printing it in the same line. So it prints 2. So the fun of 2 was also solved. Next, what you call fun of 2 minus 1, that is fun of 1. So you can see that the next record which will be pushed is fun of 1. Okay, so fun of 1 is not fun of 2 is not waiting for fun of 1 because fun of 2 has already printed 2 as an answer. Now we have to find out what is the answer of fun of 1. What will be the value of n? N will be 1. So is it if is true? No, if is not true. So it goes to else and prints 1. So it prints 1, 3, 2, 1. Okay, after that return fun of 0, 1 minus 1. Okay, current n value is 1. Okay, so fun 1 minus 1, that will be fun of 0. So you can see that it is copying last one of 0. If 1 of 0 means n value is 0. If n is equal to 0, return. Okay, so return means it's not returning anything. So it comes, so that means there's nothing to return as a value for fun of 0. So it returns an empty thing. So you can write return nothing. Okay, so that is the meaning of this line. Okay, so when you say return, what it does, it pops out. So whenever you see return, it pops out. So first function to pop out will be the last element, last function which will be inserted. So stack is something called as last in first out, which is the last inserted element. Fun of 0 was the last inserted element. So don't say that main was the last inserted element. Main was the first inserted element. So last inserted element fun of 0 will be removed. Okay, so you can see that the output at last is 3 to 1. It has printed 3 to 1. Now fun of 1. So when you printed if n is equal to 1, it would have printed 1. But when n is equal to 0, it has not printed anything. That's why it has only printed 3 to 1. So if n is equal to 0, it's saying return. Return means this fun has to be removed from the it's returning nothing. You can see the return semicolon. So it's nothing. So it just pops out. Pops out means deletes that function from the stack. So first function to be deleted will be fun of 0. The next functions to be deleted will be fun of 1. Similarly, fun of 2, fun of 3, and at last it is main function which will be deleted. So it will be an empty stack. So always when you make a function call, a recursive function call, keep in your mind everything will be stored in a stack. Okay, so again I'm repeating why we call this as a tail recursive, because a recursive function is said to be tail recursive only when if you call the function in the same within the same function only at the last line of that function. Okay, so within the body of this function, if you are calling that function within itself as a last line in the program, then such program or such function we call it as recursive tail recursive function. And one more thing is, here in each function has been subdivided, the answer or the result of that subdivision is been printed. So that means one has to not to wait till the other particular function call has been recursively solved. Okay, so that is the one of the advantage of tail recursive function. Okay, and next let us come to non-tail recursive function. It's an opposite of tail recursive function. That means a recursive call to a function can be made anywhere inside the function body. Okay, so it need not be first line, it need not be last line, or it need not be the second line. So anywhere in the program, if you mention the the recursive call, such function is called as non-tail recursive function. So you can see a recursive function is to be non-tail recursive if the recursive call is not the last thing to be done by the function. So make sure that it should not be the last thing. If you make it as a last thing, then it will be called as tail recursion. Okay, so that is what is a non-tail recursion. So here, after returning back, there's something to be evaluated. That means you can see when it comes to Fibonacci, if it solves Fibonacci of 1 plus Fibonacci of 0 in this case, you will return 1, return 0. So 1 plus 0 will be 1, and you will return that to Fibonacci of 2. 1 will be returned, but it is not going to compute the result for you since it has been solved. It has to wait for the other function call to complete its task. So in this case, it's opposite to recursive call. So what is opposite to recursive call? It says that the tail recursive call, it says that it has to wait because something has to be was left evaluated. Okay, whereas in your tail recursion problem, you didn't had this problem at all. Okay, so once you have agreed, your last function, the body of the function will contain last line as a recursive function call, and it solves that at a last point of time. Okay, so it need not wait for the other function calls. Whereas in non-tail recursive, it's opposite, where you have to wait because it has to something to be evaluated. So when you see this particular program, as usual, fun of 3. But here, if n is equal to 0, return, or else we are reducing the problem. Okay, first we are reducing the problem. That means fun of 3 is not solved. Did you printed any output? No. Fun of 3 is becoming now fun of 2. Did you printed any output? No. Then it become fun of 1. Did you printed any output? No. So you can see that fun of 3, fun of 2, fun of 1, everything. Then fun of 0, finally when you return, if n is equal to 0, what does it return? It returns nothing. So you remove that first fun of 0. If it is fun of 0 is returned, what is the value of n? So when n is equal to 0, the value is nothing is printed. So it returns blank. And similarly, if n value will become 1, it prints 1. So when you remove fun of 1, the output will be 1 because it has to wait till that point of time to print n value. And similarly, if you remove fun of 2, the value will be 2, and fun of 3, the value will be 3. But once the fun of 3 is removed, and the final thing which is left out is main function in the program. So at last, the main will also be taken out of activation record. So this is what is activation record and data structure which maintains this. And this is what is an example of direct recursive, indirect recursive, tail recursive, and non-tail recursive. So what you have to keep in your mind is that human beings at one point of time has to call a function within itself to solve the problem like recursive approach. But the thing is, once this function has been called, the function call will be stored in stack data structure, and one by one the data structure in a stack will solve the particular function definition and gets you the result. While it gets you the result, each time when it is being pushed, that will have to be popped out. So it maintains a stack data structure. So that is what is non-tail recursive. Only the definition is non-tail recursive means this particular line, that is a division of function, can be written anywhere in the program, but it should not be in the last. It should not be in the last line. If you write that function recursive call function last line, then it will become tail recursive. So that's what is tail recursive and non-tail recursive. So next, coming to the next topic, we'll see what is the difference between iteration, recursion and iteration, and then we move on with the different topics. Okay, thank you. I hope so you understood how many types of functions are there, recursive functions are there, and how to write them when the question has been asked in the examination. So you should be in a position to write the answers. Okay, so that's what is the end of the today's session.